above it are transfer dominated. And that's why it kind of got lost in folklore, so to speak. Zone bit drives and then that behavior. Now, so by default, the log is internal in the middle of the partition, but I can create the file system so the log is somewhere else. I can put it on the same drive, or I can put it on a different drive. Now, what's the problem if I put it on a different drive? If I move the log off to a different drive, what's wrong with that? Not what I'm looking for, but Lionel did this. They put all their logs on the same drive. Now, I wasn't thinking of reliability. They put all their logs on the same drive. They did not want to waste the space on the drive. Problem is when I pull that log off of that drive, what am I going to do with the rest of the drive it ends up on? I don't want it to be busy. I don't want it to interfere with this. At Los Alamos, they put all the logs on the same drive. Now all of their file systems are locked together into the behavior of that one drive. So if I pounded on one file system, created 100,000 inodes, every other file system is now going to be bottlenecked off of the behavior of that XFS log. So the problem is I've got these large drives, and what do I do with the rest of the drive now? Maybe I've got a dormant file system like var crash, var ADM crash or something. But in general, they don't want to waste the drive. So the customers are juggling these things. They don't want to waste any disk space, but they want the full performance. And they don't want to fan things out. They want to buy large drives. And that's because that's what's available. But if you get in the database market, they'll buy 4 gig drives and throw half of it away. Partition half of it as raw and never use it. And then they'll use only the inner portion of the drive where the latency is a lot quicker. Okay. And those are price-performance trade-offs. If I'm the National Security Agency, I got the money to do what I need to do, and I'll do it best I can. And I'll throw away drives. I got to say the trouble here is a lot of our customers will call us up and say, well, I'll give you $7,000 to come down and do a study of my site to tell me what's wrong. And 90% of the time you can log in and tell them spend those $7,000 on 7 more drives and spread your I/O out across those drives. Don't keep pounding on a single drive. So that XFS log has 3 ways: internal, external, or on another device. External on the same is the best in my mind. But again, that's the nature of the I/O in the file system. If I put it in the middle, I better have lots of inodes going on. And root isn't like that. Okay. If I'm dominated by inode manipulation, I want to put it for that. If I'm dominated by data being moved, I want to consider that. If I put it in the middle and I've got data movement from end to end, now I've got a problem as I keep jumping over the log. And in video, that's critical. When you're watching a video stream come up, it'll start flickering when I have to jump across the log and stuff like that. By the way, there is a command out here called disk prep. And unfortunately, it's not documented and not in the release, but it's pointed to by disk align. And disk prep will go through all your drives and set the caches and set them back to factory defaults for video streaming. And there's some good information if you go in and take a look at those man pages in 6.5. Now the other partition that we have is a raw partition that's used for 2 things primarily. The first is my swapping activity. I can mount a raw partition to swap to. And the second is for database engines. And for the database market, they do not use the operating system file system interface because it's too slow and because it's subject to abuse by anybody on the system. It's a public pool. Anyway. And there are other things that may exist on the drive. In the volume header, they got things like the label, a program called SASH that's involved in the bootstrap. There are even diagnostics, IDE and stuff like that that may be there. And the data is all my files, my directories, all that sort of stuff. The XFS log, I guess it's just saying here this partition is used only if the log is external. But that's lots of little, it's not the metadata, it's just a log about changes. It's just keeping track of changes to the metadata. And then raw data being the raw partition for swap, but database market as well. And possibly the video market, but I haven't seen it. Now these disk partitions are numbered. 0 is this is just saying a default root on a workstation type of situation. 0 is your root file system, but it's some sort of data file system. 1 is your swap partition. 6 may be /user. 7 is another user partition, 8 is a volume header, and 10 is to get to the entire disk. Now, one of my rules of thumb is minimum partitions per drive. I talked to one guy out in Boston that had 9 partitions on his root drive. /user was separate, root was separate, /user people was separate. What's the problem with that? Lots of partitions, just like I had there. Now I'm jumping all over the place to get to my different partitions. Minimum of partitions per drive. Then you're not seeking all the time and interrupting a sequential read to get to a different partition. But they had 9 different partitions. Why did they do that? To isolate the partitions from each other so I can't fill up one and impact another. Okay, so if I send a mailstorm, user mail could fill up the root file system and bring the system down. Remember that internet bug that happened about 12 years ago or something like that. If user mail had been configured as a separate file system, only mail would have broken. So that's why they separate the file systems out when they've got a single drive, to isolate a file system full condition from impacting another file system. Security audit data will often be spun off on its own file system. That way, if the system doesn't fill up, if root doesn't fill up, I don't take a shutdown to single user mode when my security log daemon can't write security logs anymore. So I normally advise people to keep it even root and user. I'd rather have them on one file system. The only reason they separate it out is for home file systems, things like that. And optional disks in the Cray world, we've always called them /temp or /work. In the SGI world, it's typically /scratch or scratch1, scratch2, names like that. And that's generally the production I/O file system. That file system is designed to do I/O. The system disk, we're looking at one here. Volume partition 10 is the entire volume. 8 is the header. 0 is root. 1 is swap. Print VTalk is going to show this. Let me see if I ever came back here. Don't have permissions. So with print VTalk, I can see how the drives are partitioned. I can do a -E and see every drive, or by default it's giving me just my root drive. And on this example, my XFS0 partition here is sector 4096 onto this sector size. I do have a raw partition for swapping. And then I see my volume header and finally my volume. So in this example, 0 is my data, 1 is my raw partition. Is that consistent with what we had here? Yeah, so that is 6.5. So 0 is my root file system, 1 is my swap. On 6.4 and older, it was actually reversed the other way. You had swap first and then root. So if you're running on the older systems, you ought to be able to catch that with print VTalk. Is it the other way around? Got it backwards, okay. Also, part of this is used for mini root. And also RoboInst is using part of it. It doesn't mention that here. And mini root is what you get, for example, when you're at the prom level and it asks you to install software or something like that.
When is partition 10 accessed?
Well, that'd be like a character device. So you could go in, it's typically not used, but there may be tools that go into it like a raw device and access the whole thing. I can't think of anything offhand, no. Oracle would? Okay. Oracle, database market. They could too, yeah. They could too. Sure. Yeah, right. Anything that's going to dump the entire drive. Anything that's going through dev disk type interfaces, stuff like that. But yeah, it's simply a way of looking at the entire contents of the drive in a raw format. The other one then, they mark it here as an option disk. For us, these are all the disks other than root. And the thing you want on a big system is get all your traffic off of root except for root traffic. So user people, user home, whatever you call it, temp, var temp, user temp, var ADM, get all those file systems off of root. More drives, the better. Volume and capacity is not what you want. It's distribution of your I/O, bandwidth. And if you're going for more than one drive per file system, you cannot use EFS. EFS can't span a single drive. That's why XFS is the default file system now. Okay, let's see. This must be HINV. With HINV, you can then look at your configuration. Now, there are a couple other tools I prefer that aren't listed here. Print VTOC is a little bit better at looking at your drives, but there is a shareware tool written by a Cray benchmarker, Paul Helvig, and it's called BSTOR, B-S-S-T-O-R. And that's not in vanilla Irix, but I use it all the time because, for example, it will give me my file system layout in a friendly, readable format. So I can do a BSTOR-P, and this is in my shareware toolkit, so let me see, ~DW. And I can generate in either picture format or HTML table format. So now I can see my file system layout in a friendly manner. I've got my SCSI numbers over here. These are the drives that have been daisy-chained deep on each SCSI. I can see the type of drive they are. These are all IBM 9 gig drives. I can see the file systems they're mounted as, logical unit numbers. I can see raw partitions and swap partitions and things like that. Okay. But I'd also like to be able to see is caching turned on and off? What's the configuration of the firmware? There's a whole bunch of things that were actually, the system support handbook had this RAID section that described a lot of these things. In terms of, is my cache set to read or write? Buffering, how many pages to the cache, all that sort of configuration information. I can also even see other SCSI devices out here. There's a tape drive out there. There's a CD drive out here, that sort of thing. And this is a tool that I'm trying to get into standard Irix in the future, but it's basically within the shareware toolkit that I provide. But HINV will give me the same sort of information for each SCSI, then I can see the unit numbers, but it's not easy for me to see what the logical file system is, see whether it's what type of drive it is, how big it is, some of that sort of information. And again, this is just trying to show that, for example, FX is a utility that is probably going to go into that volume 10 to do diagnostics and stuff. But it's trying to show that I can get to that file system either through a block device or through a character device. If I'm going through a block device, it's through dev disk. If I'm going through a character device, it's dev rdisk. And I can actually do a copy from rdisk to something else, and I'm moving stuff off the drive. Okay, but it's also generally a slower method to go through the character special files. So it represents, character special files represents a device that's accessed in units of bytes rather than blocks. And data read and written is not cached in the buffer cache, but the device driver facilitates its own buffering or blocking of the data, sectorizing of the data. And they're using /HW. Dev disk basically links into /HW nowadays. And the intent was that /HW would scale on larger systems better, so they're getting away from the dev disk interface for scalability reasons. And this is just trying to show the partition naming conventions down here. DK saying that it's a disk. S then is saying the SCSI controller that it's on. Then we've got the SCSI channel number, in this case 14. Then the disk unit number, this is saying it's a disk 5. And then lastly is the partition number, S0, saying it's partition 0 of that particular drive. And they're just looking at a couple of drives here that have both S0s and S1s. There's one here that has an S7. And then in dev disk, they're showing the same sort of thing, except here we've got VH for volume header and VOL for the volume 10 type of interface. And generally, you want your root devices lower than SCSI channel 7. If you put roots above SCSI 7, then you've got to do a couple of pings on the SCSI to recognize the device and stuff. A couple extra command lines you have to do during the boot process. are we in time? 2:30. Just about. Let's see if there's anything else in here. The volume header then is the top piece, and it's basically a special partition on the drive, typically about 2 megabyte, known as partition 8, and it contains the label, boot information like where the swap and Unix and root partitions are, a table describing the partition, the volume directory, and then there's some file space for SASH, the diagnostics, Simon, and FX. And there also may be a partition for swap space as well. And DVH tool is the tool that's reading that volume header. So here they brought up DVH tool on a particular volume header and then did a VD for volume dump, I would assume. And then you can print out the contents, giving the name of the files that are in that header. We've got a label, IDE, SASH, how big they are, block numbers, that sort of information. And print VTOC is the one that I was just showing a minute ago. And print VTOC is doing the same sort of thing, dumping the volume header. There is a -E option on it to give us all drives, everything on the disk farm. By default, it only gives me my root. And it used to, for example, it's giving here 512 bytes per sector. On older systems, it actually gave me the whole disk geometry. Sectors per track, tracks per cylinder, total size, total number of cylinders, information like that. But lately, you don't get that. I basically have to go off to cherokee.ingr to get that sort of information now. How many people have used FX? A few people. FX is the disk utility to build our drives, to format them. This disk prep will basically undo what you screwed up with FX. If you're in the video market, it resets everything to a video streaming factory default. But with FX, I have the ability to go into the drive, control its firmware, do all kinds of different things, run diagnostics. I was seeing a little bit more of FX documented in here than I'd seen before. But there's a lot of stuff within FX that are called factory options in expert mode that I don't see documented anywhere. Like how to switch the bus from 20 megahertz to 40 megahertz and turn off adaptive caching and stuff like that. There's a lot of stuff that's buried within FX that I don't think is documented anywhere. The best document I've seen has been the System Support Handbook for some of the FX options. So FX is how I can build my drives. And I think now is a good break time. Let's take about a 15-minute break, come back about 10:02. I've kind of gotten off the track a little bit more today than yesterday, so a little bit of catch up here. What I keep trying to do is apply what we're seeing on the slide to the real world, and that's where I get off track. So we're talking about file system structures and how the file system is simply a convenient and consistent way of organizing and keeping track of our files on the file system. It's mapping the file path name to the particular data and where it's stored on the disks. It has various mechanisms we're going to look at to enhance I/O performance, direct I/O, cache I/O, that sort of thing, asynchronous I/O. And ease of administration to keep track of my files, and the inodes keep track of the dates and that sort of thing. Thank you. And consists of data files and structures to find access to the data, and is created on either a single or group of disk partitions. And the file system XFS does allow mirroring of data for added resiliency. Now EFS doesn't have mirrors. To get into mirroring, we have to use XFS. Okay. That was on page 644. Now the early Unix file systems, including Unicos, and I have to admit I have not looked at Unicos 10.0, and particularly the internals of 10.0. I've used 10.0. But Unicos in general, when we had a map to locate the file's data, we were standard Unix, where we were pointing to the blocks. And now what we've got on these newer systems are called extent-based file systems, where we point to the contiguous block piece. Then we don't have to describe a bitmap for every single block, so to speak. We simply specify, we don't have to take as much space to describe the real estate. So extent-based systems, we simply have pointers to the beginning of the extent and the number of blocks in that extent. And that's a little bit different than Unicode traditionally was. So the files inode contains a map to locate the data, but we're really just pointing to the different extents. And XFS BMap is what's going to print out these extents and where they actually reside out on disk. And the point here is an extent-based file system allows larger maximums for individual files, better file system performance, and less fragmentation because you're trying to put it into a contiguous extent. Instead of manipulating an individual bit for every allocation block out there, you're going to do it in bigger chunks at a time. What Irix is missing, though, is pre-allocation. There's no pre-allocation like we have in Unicode. In Unicode, I can give it a clue and say, my file is going to be this big, please pre-allocate it for me now, and make it sequentially contiguous on the disk farm. And if not, give me a warning that you can't do that. And that's missing. So XFS, Extended File System, general purpose for workstations and servers. It's scalable. The capacity means that I can grow larger than a disk drive. And performance means that as I grow, it's not going to cost me anything to rebuild the file system if I have a problem. It came about in '94. It's about 4 years old with Irix 5.3. And it's basically replacing EFS, the previous file system. The default file system installed since release of 6.2. It's a new, fully integrated product. It's not a modification of an existing product, but they are in the process of redesigning some things about it. And it tries to address some of the scalability problems that EFS file systems had. We needed fast crash recovery as the file system got bigger and bigger. The older method of just rebuilding the directory trees was too expensive. Be able to support large file systems. There's also something called sparse files. And I'm not sure where it's being used, but sparse files says if I got a hole in my file where I don't have any data, I'm not going to allocate a bunch of zeros to it out on the file system. So it's designed to save space where files have holes in them, so to speak. Kind of like a hardware compression concept. And be able to support large contiguous files. Now, developers will say we never have fragmentation in the file systems, but in reality we do end up fragmenting files. But fragmentation occurs when we start filling up our file systems. And if you're running your file system full all the time, that's when you're going to have severe fragmentation problems. It's going to be harder and harder for it to find a contiguous piece. But it's going to try to do the best job it can to get that file in one contiguous piece. Support large directories with lots of inodes in the directory and be able to support large numbers of files in the directories. And there's something that we don't use in Unicode called a B tree or a binary tree to increase the scalability. Now XFS is also the first 64-bit file system, so I can address with large files and large file systems and large numbers of files. Everything else was a 32-bit file system before. And again, this sparsely allocated file where the file has holes where there's no data in it. Rapid and reliable recovery of the file system using journaling technology, and I would have to agree with that. Some of the large, like Saudi Arabia sites, will have half a day to rebuild their catalogs when they take a serious corruption of the data. The problem here is that we're taking the penalty as we're doing meta manipulation rather than when I boot. On Unicode, we take the penalty when we boot. Here, we're taking the penalty as it occurs. But I haven't seen it cost anything. It hasn't shown up as a wait time or anything like that until you actually get lots of inodes, such as news servers, where it becomes a problem. This benchmark where I was mailing 200,000 email messages onto a machine. That's when we start having problems. And frankly, the Starfire that we sold off the Sun, we were running 45 minutes on the Origin, 15 minutes on the Starfire to do the 200,000 email messages. And a lot of that was all directory manipulation type stuff, working with those inodes. And 200,000 email messages, 3 or 4 inodes per. That's 100,000 inode, or 200,000. That's 1 million inodes on the system. 20,000 emails, 4 or 5 per email. So you're trying to create and destroy 1 million inodes as quickly as possible. And journaling can start showing up in those scenarios because I've got lots of metafile construction and deconstruction occurring at the same time. There is what's called an integrated full-function logical volume manager called XLV. It's a layer underneath XFS. XFS is looking more towards what's coming from the applications and is part of file system buffer cache. Whereas XLV is the geometry, the striping and mirroring that's the disk-oriented side of the drivers. So look at XFS as in terms of what the users are seeing, and XLV being what the disk drives are feeling. They're basically taking their side of the problem. Extremely high I/O performance that scales well on multiprocessor systems, but you got to have the file system to back it up. And for example, writing to RAID 5s is a bad thing to do, because then you spend all your time with write penalty, generating fire codes, things like that. Now there's something that's not being used in the typical Cray market, but it's used in the multimedia market in particular, in the real-time market. That's called guaranteed RAID I/O. This is their version of primary and secondary. The guaranteed RAID I/O would be like a primary partition where all my guaranteed controlled I/O streams are going. It's almost a reservation mechanism such that I cannot abuse that particular file system. And again, if I had different types of drives, I put the drive with the lower crossovers on the real-time portion and put the drives with the bandwidth configuration on the normal data portion of the file system. Just like in Unicos, I'd pick a smaller crossover for primary and a larger crossover for secondary. And it was pointed out during break, you want all the drives in the configuration of that file system to be the same kind of drive. As somebody was talking about during break about RAID devices, if you lose one of the RAID drives, it's the same part number for both an IBM and a Seagate. But then when you put it into the cabinet, it's not going to behave the same, and the RAID cabinet is going to have a performance problem because you stuck a Seagate drive into a IBM RAID configuration. And we say the same thing within Unicos. Don't mix drives within a stripe group or anything like that. Have them all the same drive, configured identically, as symmetrical as possible within that configuration. And as I was pointing out before, disk align is a command to build an XLV configuration for video streaming, but not for database. And it will reset all your drives, or all the drives specified, and configure them for a data streaming situation. It'll turn off read cache, turn it on to write buffering, drop the cache configuration to one cache line within that cache that's in the hardware cabinet, all kinds of things like that. So look at the disk align man page. It's worth just reading it. Just remember, it was written in the entertainment industry for video streaming situations. And if you're mixing in the file system, it may be bad for you. Backup file systems while still in use, XFS dump. And there are some problems in this area because there's something called attributes or capabilities. And those aren't necessarily dumped with tar. XFS dump is the only thing that can dump out the attribute type of information. And XFS is compatible with existing applications, EFS and NFS. Maximum file size is 9 million terabyte. Maximum file system size is basically unlimited, but number of drives you can plug onto your system. The file system block size, when I do allocations on the file system, it defaults to 512 bytes. It's the smallest block chunk that I can do. But the actual default is, I think, 4 KB. On your workstation, it might be defaulting to 512, and then on the origin, it's defaulting to 4 KB. And 4 KB is where Cray has always been, except in some of the newer drives, or not new now, but DA60s and stuff like that, they went to larger block sizes and larger sector sizes. So this block size can go from 512 bytes to 64 KB. Remember, 64 KB is the friendly number. Okay, and up to 1 megabyte. We can go up to 1 megabyte in a real-time file system, or GRIO, Guaranteed RAID I/O file system. And when you make the file system, you can specify the allocation unit size or the block size. So if I was on a news server with news articles, I'd go with a small block size, because my articles are typically a KB or less, and I got lots of them. Whereas if I've got a terabyte video movie that's coming up, I would be going to large allocation units. Number one, to save the map space. So I don't have to take as much real estate to keep track of the allocation of that file. Physical sector size is 512 bytes. Mountain View says it will be going up in the next XFS revision, probably to 4K byte. And we've been at 4K byte and been upping it from there. It supports an extent or a single piece of the file from 512 bytes up to a gigabyte in a single extent. So if I have a 5 gigabyte file, there's going to be at least 5 extents, at least 5 contiguous extents for that file. There may be more than that, in which case the extents are not contiguous. They got broken up into pieces. But the largest single piece we can have is 1 gig. You can have EFS and XFS active on a single system at the same time, so some drives could be mounted EFS, some could be mounted XFS. Normally you don't do that. However, you may have a workstation environment where your root is still EFS, but you've mounted an optional stripe group to do like video I/O or something like that, that would then be XFS. But the Cray market, you don't see them both on the same machine. And then XFS dump, XFS restore to do my backups, BRU. I had a guy at Llano that was complaining about performance of his machine. Every time I logged in, it looked fine. Then I happened to turn on accounting and stuff and saw file system backups. Every time he had a performance complaint, it was because BRU had been fired off by a cron event. And he had a single drive system. So that disk drive was busy doing backups, and then he felt the performance effect. But he thought, I need more CPUs, I need more memory. Again, disks are the things they're bottlenecking on these days because they buy large disks rather than lots of disks. And they're not interleaving and fanning out the I/O like you'd like to see them do. EFS and XFS dumps are interchangeable, so you can dump an EFS and load it into XFS. You can dump an active XFS file system. No guarantees on what you pull off of it, obviously, if a drive has got corrupted data or something. XFS supports mirroring, striping, and what's called concatenation. I've always called that banding in the Unicos world. When we banded drives, that's basically concatenating the drives into a larger file system, but without striping or mirroring. Okay. And again, mirroring is for what? It's for reliability of the data. Now we can get into mirroring SSD file systems or volatile devices. For example, there is a SCSI SSD device available out there, but I don't know of anybody doing anything like that. So we could mirror a volatile device like a SCSI SSD to a solid state or to a actual disk drive to protect it. And then hopefully see the speed of the SSD, not the disk drive behind it. And some sites did that in Unicos with SSDs as well. But in general, other than that, mirroring is not necessarily a performance event. Some people pointed out that you're going to get reply from whichever mirror answers you first. So you may get a little bit of performance benefit there. But in general, we're not doing mirroring for performance. We're doing it for reliability. And then striping, the reason we do striping is for bandwidth. Not for latency, not for speed. We're doing it for bandwidth. So we got into disk arrays and striping. And the wider the stripe, the wider the bandwidth. If I'm moving hello mom 9 bytes or something, I'm going to activate all the drives in that stripe group and single thread myself and treat it like a single drive. So again, it's like wasting bandwidth. I've got this huge data pipe set up by striping 120 drives wide or something, but then I write 9 bytes and only use 1 drive of the entire stripe group. And this is the problem that we're getting into, where they're putting homes in with RAID 5 devices and large stripe widths, but they're doing lots of little I/O. And then it's like me in the moped between the 2 semi-trucks. Somebody gets stepped on. And the moped is the one that usually gets marooned or pushed off the property, so to speak. So I see a lot of abuse with striping, where people are over-striping thinking that that's the greatest thing in the world, but it's only as good as the request size. If I'm doing lots of little I/O, I'm going to be wasting bandwidth. Okay? And this is true in the Cray world as well. So the other option now is concatenation and to put those drives together as a single file system. But there's nothing good in Irix to do distribution round robin among the physical drives like we do in Unicos. So in Unicos I can say every time I create a file, put it on the next physical drive. And then you configure it such that every physical drive is on the next SCSI rather than all on the same SCSI. And then you can spread your I/O across all these different drives. So concatenation does not guarantee that distribution at this point. So a lot of people go to striping instead of concatenation to try to distribute and spread their I/O across all those drives. But if I'm doing lots of little I/O, I'm only going to pound on the first drive of the stripe group. And a lot of the software is doing stripe alignment. So whenever I do my I/O, it's going to get aligned to the first drive of the stripe group. If I move 9 bytes or 90 bytes, they're all just going to go to the first group. Anybody remember what the default stripe unit size is? What was the friendly number? 128 blocks is correct. And those are 512-byte blocks. It comes out to 64 kbyte. So if I'm doing transfers under 64 kbyte, I'm only going to pound on the first drive of that stripe group. I have to get a transfer over 64 kbyte to be able to break it up into 64 kbyte chunks and then send it off to the drives in the stripe group. That's the only way I'm going to get parallel striping operation. So an example of an application that's a database engine doing credit card transactions, since it's a 4 kbyte transfer, behind the scenes I'm moving 64 kbyte chunks. And they're all pounding on the first drive of the stripe group. That's where your striping is going to hurt you. But the problem is concatenation doesn't guarantee any distribution. What we really need in the file systems is primary, secondary allocation, contiguous pre-allocation, and also round-robin techniques with a concatenated file system. Those are 3 things we did in Unicos to solve some of these issues, to segregate traffic out.
Dave, are you saying that with concatenation the way it is right now, that it's not going to go?
There's no guarantee as to the distribution.
Oh, but it's not a case where it's going to wait until it totally fills up, say, element 0 before it starts using element 1.
No, we have to get into what's called allocation groups. We do have a round-robin allocation group by directory, but not by file. So that's getting into a couple slides in the future. Now in SGI word, mirroring is called plexing. So if you plex something, it's the same thing as a mirror. You create a plex of it. You're limited up to 4 plexes or copies. You're also, when you put these things together, limited to 128 volume elements to create a file system. Okay, and a volume element is basically a Unicos partition. So a volume element could be one drive where I've got one XFS partition per drive, 128 drives. I can put them all together into a single file system. And I can put them together as a stripe group, concatenated, or I can do mirroring. And there's a concatenation limit of 100 partitions per volume element. In fact, one of these sites, Novel, down in Mississippi, was doing 4 disks wide, concatenated 4 times. So they had 16 drives. And rather than doing it a 16 stripe group wide, they went 4, 4, 4, 4. Unfortunately, their I/O would have been better off 2 8 times rather than 4 4 times. Because they were too wide, 4 disks wide, they were not doing I/O that large. They had an application that was pounding on the file system but doing little I/O. So the striping wasn't helping them, it was hurting them. So you got to make sure you pick your stripe widths properly, and then you can concatenate whatever you need for your capacity. Unfortunately, at the site, they also did something bad. They went 4 4 4 3. And the last volume element group, or the last logical volume, was composed of 3 drives rather than 4. Unsimilar geometries. It would confuse XFS and create all kinds of problems in their file system. You want everything to be as symmetrical as possible when you're doing striping. And you want them all to be the same drive, all configured the same way, hardware caches configured the same way, all that sort of thing. Now there are dynamic changes allowed, so I can add and remove mirrors on the fly. I can extend a volume. If file system fills up, I can add space to it on the fly while it's running. And I can replace failed volume elements of a volume depending upon what's on them and where they are and how catastrophic it is. There's always a no-win situation, but it does it pretty good. Now XFS does do something new. It's called a B tree. In normal inodes, we just chase down a single link, but B trees are used in XFS to make things quicker. And basically, we're looking at here, what file were they going to look for? They have a sample here where they were looking for lib, or okay, yeah, they've got a path here where they're trying to get to a directory down here. So when we go through the search, I alphabetically look at it, and I've got 3 different pointers. One for the A through C, for example, H through K for the second piece, and then O through S for the third piece. So depending upon where my sort falls in, I may take 3 different paths to search for things. And it just allows me to traverse the inode tree much more quickly and reduce my search times. So it's a data structure that maintains an ordered set of data and allows more efficient operations to find a key. Node records containing the keys and pointers that link the nodes together. A B tree can be designed with different number of keys per node, and the example B tree has 2 keys. The keys are kept in sorted order. Okay, and let's see. So if we wanted to locate the file name lib in this B tree, we begin at the node root. Lib is not there, but sorts between dev and mount. So we follow the middle pointer to the next subnode. Lib's not there, but it sorts after KKG, so we follow the pointer to the right to the next subnode and get to lib. And I'm not sure why, well, they were just getting to this particular library here. Okay, so XFS, we've got the system call interface to manage it. So reads and writes are going to call the IO manager. The directory manager would be if I'm opening and closing and unlinking files, manipulating the inodes. And then we've got, I'm not sure what they mean by the space manager or transaction manager, but the buffer cache then is my file system buffer cache. This is really XFS. And then underneath that is my volume manager, which is the XLV that understands the geometry of the disk drives. And then lastly, I've got my disk drivers underneath. Now what's it referring to as terms of a space manager? Allocation space and transaction manager? I'm not sure what.
Next page.
Let's see.
Space is talked about on the next page.
Yeah.
My next page.
Yeah. IO manager is taking care of the requests, but it's going to use the space manager to do the allocation and deallocations. And the directory manager implements the file system namespace and the directory name lookup cache, translates path names into file system references, and it's using the B tree to get through the directory, to traverse the directory. So the space manager is what they're describing, basically what allocates and deallocates and manages the file system. Responsible for efficiently allocating space within the file system, is going to try to make things contiguous. It's going to manage the free space, allocation of inodes, and allocation of space within files. It's what's actually going to map a file to the sequence of disk blocks. Figure out where does it belong. It controls fundamental structures of the file system. We've talked about inodes and free space. There's also something called allocation groups. Whenever I try to allocate a file, it's going to go into a particular group, and I can round robin among those allocation groups. And we got some slides coming up on that. It uses B-tree technology to represent the structure of the files. It divides each file system into allocation groups. Each group has a collection of inodes and data blocks, as well as structures to transverse through that allocation group. It gives me dynamic inode allocation, for example, if the file's in line with the inode. And it's going to try to optimize the layout of the blocks in the file to avoid seeking during sequential processing. It's going to try to make it contiguous. Now here's my thing about contiguous versus non-contiguous. High intensity I/O applications are probably going to be able to get a contiguous piece. And the reason for this, not documented here, XFS does what's called a delayed reservation technique. It's going to hold off the allocation until the last second. If I have a high I/O intensity application, I'm going to be able to sock it into cache, and it will have a better idea of how big this file is going to be and be able to more accurately get a contiguous piece. But if I'm in the database market where I don't have high I/O intensity, there's a good possibility that I'm not going to be able to create the size of the file in my cache real quickly, and XFS would not be able to create a contiguous piece anymore. So I'm going to start off small and then grow. TAR might be an example of that. I start off small and then I've got to grow. So I'm going to get an allocation, but then as I grow I've got to reallocate, and I may not be able to get it contiguous anymore. And this is what we need in what we have in Unicos that we need in Irix is pre-allocation, so that I can give it a hint as to here's what my size is going to be. Try to allocate this for me now, and then I don't have to fragment my file system to get that contiguous piece. The other thing that's nice about Irix in this area, that Unicode doesn't do very good at is this cache can grow and shrink. So if I've got this big file and I sock it to the file system buffer cache, it's got extra breathing room to absorb that file and get the whole file in cache and therefore have a better idea of how big it's going to be. Whereas if I'm in a small cache, I may be fragmented where I've got lots of little files breaking up my cache and I don't have the breathing room to suddenly take all of the available memory in the system, hold this I/O file that was delayed write, and now allocate it. So that cache, this breathing nature allows me to get the whole file into cache before I actually have to do the allocation. And again, the higher the intensity, the quicker I can get it into cache, the better idea it has of how big the file is going to be. Whereas if I'm trickling it out there and the file is growing slowly, it's not going to know how big it's going to be and it's going to end up fragmented. And fragmentation means I'm going to be jumping all around to read that file. And if I generate a Disney movie and then 15 different people try to play that movie off of a web server, I'm going to be slowing things off as it's constantly trying to, reposition the data into a sequential piece again. And flickering in video is one of the quickest ways of spotting fragmentation.
Does the Irix set container defragmenting tool?
No, there's no defragger. We avoid fragmentation in the first place. And software says we don't fragment files. Of course, it does happen. And the problem is that as the file system fills up, everyone's trying to save disk space and disk money. So they're running their file systems full. They're also saying, well, this is a big file system. It's a RAID cabinet. But you're still running at 95 to 100% full, and you're still going to have fragmentation problems. By the way, for people that are familiar with fragmentation in Unicode, the metric is derived different. With df-p in Unicode, you get a fragmentation number. It's different in Irix. In Unicode, it's a property of number of blocks, number of free blocks, and how much space is left in the file system. So as I start filling up my file system, I start fragmenting. Whereas in Irix, it's simply the number of inodes that contain more than one extent. It's a completely different way of calculating that number. So my rules of thumbs can't map to the two different derivations. But in Unicode, we said 10% or less. And a lot of these sites would start having problems and become I/O bound when they had fragmented files that everyone was constantly reading off of or something like that. So it's going to try to provide optimizing the layout of the blocks to avoid sequential or to avoid fragmentation so that I can get sequential processing, good for the video market. And then it keeps related files close to each other on the disk. No, that may be good, but that may be bad. I may have an application that's got 3 scratch files. In Unicode, it will default to the next disk. In Irix, it will default to being near me in the same disk. So if I open up 10 files, I'm now competing with myself on that disk. Whereas in Unicode, we've got round robin by file. I would be able to spread it out among the different disk drives, and then other people are competing with me, but I'm getting good bandwidth. And lastly, it's going to try to use large extents to form contiguous regions in a single file. Yeah.
What do they kind of represent with this diagram?
Just the different layers. I make a system call, and depending upon the system call I want, I'm going to actually do reads or writes, I'm going to allocate space, or I'm going to create the file in the first place. So it's just trying to show the layers of software as I'm going down.
Okay, so the I/O manager is really on 3 layers? Is that what you're saying?
It's eventually going to pass off the issue to buffer cache layer, correct. Okay. So these are the ones that are actually doing the I/O. These are the ones that are managing the I/O request. So if I do a read or write, the I/O manager may have to go to the directory manager to create the directory or file if it's not there. It may have to allocate space, and the transaction manager is what we're going to look at now. Eventually, once I've done that, said that I/O can occur, then I pass it off to the buffer cache layer. And then buffer cache is going to pass it off to the volume manager, which is going to sectorize it and send it off to the disk drive in a friendly number based upon the geometry of that disk drive. And by the way, this volume manager in XFS may not have any ideas to the geometry of RAID cabinets underneath and how they're put together. So we can give it clues in 6.5. And there is an extremely useful set of options in 6.5. Look at your man page for FS tab on 6.5. You can turn off logs. You can do a variety of things, including controlling the size of these buffers. Anybody remember what I said the size of those cache buffers were? 64 kbyte, good old friendly number. Just like the volume manager defaults to 64 kbyte. But if I'm doing 4 kbyte transfers here, everything down here is moving things in 64 kbyte transfers. So I may want to drop the geometry down if I'm doing a 4 kbyte transfer for a database engine. So when I mount the file system, I can give it clues as to these geometry questions. And one of the things I can tell it is say, don't make those buffers 64 kbyte, make them 4 kbyte. Now what does that do for me? Less I/O load, I'm not shuffling around 64 kbyte anymore, particularly if I've reconfigured the volume manager to narrow my stripe width and narrow my stripe unit size, drop that down. Okay, but the other thing is the footprint. If now I'm doing 4K instead of 64K, I've got less memory space, but in actuality what I can do now is have more buffers in the same footprint. Okay, so now those 125,000 buffers, I always take nbuff and multiply it by 64 kbyte to get worst case scenario. And this is almost like LD cache. With LD cache we can set the size of the pages. But what's missing here is I can't say how many buffers does that file system get. So when I mount the file system in the mount table, there's a BIO size. And I can say drop it down to 4K. But I can't say how many buffers out of your large pool can you use. If I had that other piece and said number of buffers and say I'm only going to use maybe 100 buffers on that particular file system, then I can isolate the buffer cache from that file system and prevent it from taking all of the buffers for one I/O request. And this is something that the LD cache did for us in Unicos, was segregate our I/O such that I don't have one thing abusing another file system's I/O paths. So you can mount your file system and drop the size of that buffer cache down. But then you also want to fix the volume manager to drop it down. And in the disk drivers, the firmware in the disk cabinets, you want to change the disk cache configuration to match that same size. All three of these are at 64 kbyte by default, and that was just picked as a middle-of-the-road friendly number. So in lots of little I/O, I drop it down. Unfortunately, in big I/O, I can't go up. Okay, for example, Nastran, the largest I can do is a 64 kbyte transfer through cache. If I want to go to larger transfers, then I have to bypass cache and go straight to the volume manager. And that's referred to as direct I/O. And when I do direct I/O, I want the stripe width, what that disk drive, that stripe group can take up in a single request to match my request size. And when they get great bandwidth out of file systems and say, I got 128 drives striped here, they're testing it with a transfer size that matches the stripe width. Okay, they're not testing it in real world numbers, they're testing it in, I'm going to give you a friendly number that you're configured for. Well-formed I/O is what it's been referred to in the Cray world. And I'm just calling it also friendly I/O. Unfortunately, NFS, for example, does 32 kbytes, but we take a 64 kbyte footprint for it. So we're just talking about the different layers as I have to do work on the file system, and the system call was what started this based upon whether I'm manipulating the data, manipulating the pointer information like inodes and directories, or trying to do allocation. And I didn't really know what was meant by transaction manager, so I'm just looking here. Transaction manager is used by the file system to assure updates to the file system metadata. It's what's taking care of the journal to keep track of my logs and stuff like that. So as I'm doing actions, the transaction manager is what's keeping track of all the control structures for the file system. Okay. So it's taking care of the XFS log, it's taking care of flushing inodes to disk to make sure they're current, that sort of thing. And then buffer cache is used by all other file system parts. It sits in memory. Contents are frequently accessed blocks, hopefully. It's integrated a single cache which has both pages from vHAND being stolen and file I/O, reads and writes, going through the same cache logic. We're sharing the same threads. As far as I was concerned, memory shortage and paging is an I/O operation. And we don't know whether it's read or write or memory shortage that's causing that pressure, that's causing that page to get pushed through the cache. And again, by default, everything in Irix goes through buffer cache except things like backups. XFS dump, BRU. They will be doing direct I/O because that's what they do in life. They go to the disk and dump it off to tape Okay? We don't want that cached. When we want caching is when we're going to reuse the data in 100 seconds or less. That's when we want caching. And lastly, then the volume manager is what actually understands, it's communicating between XFS and understanding the underlying disk devices themselves and the geometry there. And it's what's providing the striping, the concatenation, the mirroring. It's handling the geometry side of the question to the drives itself. And it's separating disk management from the file system to simplify the implementation so that we can have several file systems implemented there. So XFS is composed of the data section with both data and your metadata. All your inodes and directory information are there. And there's a parameter VFS sync that's flushing the stuff from memory to disk to make that current. Then we've got the log section, which is holding the journal, and it could be internal or external or on a separate drive. And we may have an optional real-time section. Real-time, again, is virtual reality or something like that, multimedia markets. And what are we showing here? We're just showing simplest case where the data and the log sections are combined on the same partition. Or in this example, they've got a data portion on one drive, a log portion on a second drive, and a real-time portion on the third drive. And again, the problem is that the log is not very big. What do you do with the rest of the drive that you put the log on? You don't want to put all your other logs there, because then all I have to do is create a bunch of inodes in one file system, and every file system then locks up as I try to keep my log up to date with whatever I'm doing in other file systems. So makeFS is how we create the file systems. There are a whole bunch of options there to set up block sizes, things like that, inode allocation sizes. They can all be modified later with XFS GrowFS. XFS GrowFS will print out these attributes and allow you to modify them on the fly. And the first makeFS option here is the B option for block size options. When I do an allocation, how big is my block going to be? The minimum value for the block size is 512, which turns out to be 64 kbyte. That's the default for my data portion. Okay. And here again, we're just trying to save space. If I got to create a terabyte file, let's not do it 512 bytes at a time. Let's go to larger allocation blocks. If I have lots of little I/O, like a newsreader, I would not want my allocation blocks to be too big, because then I'm going to end up wasting disk space. If my news articles are typically 1 kbyte or less, and I up the transfer size to 64 kbyte, I'm going to be wasting 60 kbyte on that drive, or within that allocation unit. I'll end up wasted space. The trade-offs with block size options are fragmentation versus time it takes to do the allocation, and the memory footprint it takes to describe that allocation. But if I pick too big of a size, I may also get into fragmentation, where I can't find contiguous pieces for my little files anymore. And that's why we got into primary, secondary partitions, so I could have different allocation units. Small allocation units for small files in primary, and large allocation units on the stripe portion in secondary. And again, in the future, the block size will be going up to 4 kbyte. The D is specifying my data section options. I'm waiting here, 63% back. Must be a drawing, is it? I don't know. So the D option is specifying my data sections. And in this example now, we're starting to get in what are called allocation groups. So this has a disk partition divided into n equal-sized allocation groups. And then when you create directories, each directory is going to go round robin to the next allocation group. The distribution is by directory, not by file. Now, another thing to keep in mind here is that the allocation group, a file cannot span an allocation group. A file has to fit into the allocation group. So if I have too many allocation groups trying to spread it around too much, I'm going to end up with too small of an allocation group, and it may be hard for me to find a contiguous piece, because I've broken them up into too many pieces. Plus, I have to go through more and more allocation groups looking for contiguous space. Okay, but if I don't have enough allocation groups, then I'm not able to distribute my I/O across the file system. So we've got what's called an allocation group count, AG count. It says how many allocation groups do I want. You don't want it too big and you don't want it too small. And again, a file has to fit into the allocation group. The minimum allocation group size is 16 megabyte, and the maximum is 4 gig. So setting a count to a large number should be avoided, since this causes unreasonable amount of CPU time used when the file system is close to full. What happens here is as the file system fills up, I now have to look more and harder to find a contiguous allocation piece. And as file systems fill up, you will get a slowdown or a throttling back effect on the file system. This is not intentional, it's due to the allocation groups. Okay. There's an I option for inode options. It's just specifying the default inode size. The default was 256 bytes as a minimum, and we can go up to like 2 KB. So it's a variable part of the inode that can contain, after the inode, we've got a space that allows us to have small local files, directory data, symbolic link, an extent list for the file, and also the root of the B tree for that particular inode. And then we have the log option, -L. In this example, they're doing the simplest case, making the log internal. We already talked about how that puts it in the middle of the partition. And it doesn't really specify that here, but it goes in the middle. The thinking being that I'm always halfway to the log. And that would make sense in a news server situation where I'm always going to the inodes, not the data. If I'm always manipulating inodes, then I'd like to be close to the inodes all the time. But if I'm always reading data, I don't want to be interrupted to go off to the inodes. The R option is to create a real time, so they've just done a -R here and created a data section on one drive, log on a second drive, and a real time partition on the third drive. And again, the real time is almost like a primary concept within the Cray world. Primary, secondary is real time and data, because they're slanted more towards real time. So when I create the file system, I get these allocation groups. And again, let's see, additional attributes of an allocation group is from half a gig to 4 gig. Each has its own data structures. That way I'm not locking on another allocation group thread. I can have activity going on in my different allocation groups. If I'm creating an inode, if it's in a different allocation group, that's to my advantage. It has pointers to the data and the inodes. And let's see, relative to the allocation group, so it can be much smaller, they're using 32-bit pointers within the allocation group. And again, the control structures are independent of those in the other groups. So in an NFS environment, in a news server environment, having lots of allocation groups for small files is to my advantage. And then free space and inode management operations can proceed in parallel throughout the file system. In other words, it's multi-threaded. Processes running concurrently can allocate space in the file system without interfering with each other. So they're all segregated into their own allocation group. And we really don't need to get into this bad here, but this is looking at the beginning of an allocation group where we've got a couple of blocks here. We've got a super block, 512 bytes. And then there's an AGF, an allocation free block pointer, and an allocation inode B tree pointer, and then the internal free list, just for that allocation group. So we had a number of blocks, but then we had a list going through it. And then here we've got a free space B tree ordered by block number, but we also have a link through it ordered by the block size. So when I'm trying to allocate within the group based upon my size, I can go through these and look for big or small and try to put it in an area where I will not get fragmentation. Again, there's no defragger. Defrag is basically garbage collection on your disks. And we really can't keep defragging file systems. As they get bigger and bigger, defragging just is a dead end. You want to avoid the fragmentation in the first place. So the super block is replicated in each allocation group. Then we have our group free blocks, points to the structures for locating free space. Then we've got the group inode tree, points to the inodes within the group. And lastly, we've got this internal free list for the B tree management. And there's a command called xfsdb that allows you to chase through this stuff. So in the super block, our structure basically has the block size, which would be like 512 bytes, number of data blocks within this group, where's my log, what's my inode number, the root one that I'd be mounting the file system with, the size of my allocation group, number of groups I've got, number of blocks for the log, what's the size of an inode, how many inodes can I put in a block, and then there's number of allocated inodes, number of free inodes, and number of free blocks on the system. So that's the kind of information found in the super block. And again, it's replicated in each particular allocation group. And this is just trying to show the allocation group free blocks. Got a pointer off the group free, pointing off to blocks. Let's see if there's any. XFS has replaced the more common free space bitmap. This is what we've always used. We've used a free space bitmap for our allocation schemes within Unicos. But now it's basically done with B trees here. Saying that B trees are a more fast and flexible method of managing the file system. And this is trying to say block zero's allocation group free list points to two B trees, one B tree ordered by block number and one B tree ordered by size. And this allows XFS to find free space of a given size and helps to keep files contiguous. So XFS dynamically allocates inodes as needed, permits greater performance because the inodes can be positioned closer to the files and the data that uses them. Fewer disk seeks if we put the inodes close to our data. And again, it replaced the inode bitmap with B tree. And each entry in the inode B tree block represents a chunk of 64 inodes. And I think that it's saying the next page just kind of lays that out. So within here, we've got a whole bunch of inodes within a block here, B tree pointing off. So when you do a makeFS of a default of 96 byte blocks, you're getting 256 byte inodes in there, and therefore 64 inodes in a chunk. So the XFS inode is how we get to the file. Inodes have a length that's specified as an option to the makeFS, 256 bytes to 2K. Divided in two parts, the fixed size part, which is the actual pointers, and the variable size part that may contain the data or extent lists. And the primary purpose of the variable size portion is to hold the data right in the inode, so I don't have to go any further if I find the inode. And again, knowledge of how a file system is going to be used is useful to configure the inode size of a file system. It's really not the inode size that's critical, it's the data size. Because if you get too big, you get fragmentation and wasted space. If you get too small, it takes a long time to do all the allocations. Let's see. Nothing else there. So it's just breaking out the fixed size of the inode here. We already talked about this, the magic, the mode, the version, the format. The format's blown out here saying that 1 says it's local data, 2 says it's extents pointing to the data, or 3 says it's a B tree root block inode, and there is no data. So the data portion can be local data, can be directory data. Short, by short, I think it means it's not long names, just the first portion of the directory name. You could have things that are more than 16 bits wide, and then you've got a long directory name. The data portion can also contain the extent list, the B tree root block, and also if it's symbolic link information. Now on top of this inode, we've added some new stuff called attributes. Attributes are how I can tag a file to say that it's like a showcase file, such that when I click on it, it knows what application to load. That's one way that I know attributes are being used. So I can mark this file with given attributes, and when I click on it with the GUI, it'll know what particular application to fire the thing up with. Nothing else there really. And this portion now is trying to show the inode extent list where we've got an offset starting block and number of blocks. So they're trying to describe a file here. Again, in this case, they've got a block size of 4 kbyte. The file is split between 3 different disk drives. There's one extent on the second drive. There's one extent on the first drive. There's a hole, no data there. And then lastly is a third extent that's on a third drive. So the extent descriptor basically is giving an offset, the logical position in the file where the extent is positioned. And then we've got the starting number and the number of blocks. Well, let's see, the design allows something called holes. This is not something we've had in Unicos either. But basically extents are designed to skip logical space within a file that's a hole. And the resulting hole consumes no disk space, but will be read in as a sequence of zeros when I read it in by a process. This is almost a hardware compression on the file system. And to print all this stuff out, as I mentioned earlier, XFS BMAP will print out my extent list and will give me my fragmentation information. This is the same thing as FCK on Unicos. So if I've got a movie that's jumping around when I'm trying to display it visually, I can run XFS BMAP on it and see how it's physically placed out on the file system and see if it's fragmented or not. So in this example, we're looking at, they did it on ITSI, so they've got 1, 2, 3, 4, 5, 6, 7 different files here. This UTemp-X appears to be the one that's most fragmented. So I've got 5 extents to it, and these are the address pieces. Looks like 8 blocks a piece. So I've got 5 times 8, 40 blocks spread across 5 different places on my disk drive. Okay. And that would be fragmented, whereas these others are not fragmented. They all exist. This one is 40 blocks, but it's all on one drive in one contiguous piece. Okay. I think this is the last piece then, attributes. Now we've got journaling a little bit in here too. So attributes, we can give an attribute name. The name has to be less than 256 bytes, and then we have to have a value. The attributes area of the inode allows the user to match a name-value pair to objects within the file system. Attributes can be attached to any type of inode. The purpose of the attribute is to store meta information about the data, about the file. Okay, let's see. And there's 2 separate attribute spaces in each inode. One is for root and one is for user attributes. Users will not be able to modify the root attribute space, and then the user attribute space is protected by file permissions. So it's based upon chmod. And do a man on ATTR to look at file attributes. Now the allocation strategies, and this is something that needs to be understood quite a bit. XFS tries to allocate space for files in a manner designed to enhance I/O. XFS uses the following schemes. First of all, each time a directory is created, it's placed in a different allocation group than its parent. So we're going to try to distribute our directory creation among the allocation groups. That would be like a MakeFS round robin by directory type of concept. Once a directory is created, XFS attempts to cluster the inodes in that directory and the blocks associated with them around the directory itself. Try to keep them all close together. And then directories of small files are then clustered together on disk because the data is going to be right in the inode, right in the directory. For larger files, XFS attempts to allocate the extents initially at the file's inode and afterwards near the existing block in the file that is closest to the offset in the file. So it's going to try to do a fit. And then blocks will be allocated near the last block in a file for users sequentially writing, and near blocks in the end of the file for users writing into holes in the file. I'm not sure I understand that. We'll go on. Files or directories are not limited to allocating space within an allocation group. I thought that was not true. directories I can see, but I was told that a file cannot exceed the size of a single allocation group. I would put a question mark next to that bullet. I don't know for sure. And files and directories are file system global structures that reference inodes and blocks anywhere in the file system. So. Now in the log, we've already talked about the simple case. Data log are combined in the same partition. It's in the middle of the drive. And if you look at FS tab, by the way, there are options to turn off the log or even change the size of the kernel buffer where this log activity is. We don't want to stripe, for example, if I put that XFS log on a separate drive, we don't want to stripe it because there's lots of little I/O. However, if I increase the buffer size in the kernel, I could increase that to a stripe width and then be able to get that log data going more quickly off to a stripe group. So if I've got lots of I/O operations going on, I may want to hold it in my memory buffer before I actually say move it off to the XFS log. And let me go off here for a second. By the way, just a little point here. To ensure maximum performance, we have to consider the hardware, the disk driver, the striping operation, page alignment, direct I/O alignments, and then application-specific request sizes. And what I was going to do here, where was I? Oh, FS tab. So if you do a man on FS tab, there are a bunch of options here. For example, log buffs will set the number of memory in log buffers. So if I do start striping, I want that to match my stripe width of my log partitions, however I put them together. The default value is 8 buffers for file systems with 64 KB block sizes, 4 buffers for 32, 3 buffers for 16, and 2 buffers for all other default configurations. Increasing the number of buffers may increase performance in some workloads where you're doing lots of metadata manipulation. Okay, then you're not always pressuring it out to the disk drives. And of course, it's going to cost you extra memory and log buffers. But I can also say no recovery and completely turn off the XFS log activity. And file systems mounted no recovery must be mounted read-only. So that'd be appropriate, for example, in a web server environment where I just load the stuff on and I'm not constantly changing the data. And did I see BIO size? We also talked about BIO size here. It has to be in powers of 2. Now traditionally, I might point this out, historically the way we did it was we wrote the application to buffer to the disk. So we had a lot of applications out there that were designed for DD29s, for example, that had 48 blocks to a track type of rotation, and all these applications would actually buffer their data in 48 block chunks and then do their I/O requests. But then we started getting into zone bit drives and LD cache in between, so the next thing we started to do was put in caches. In original Crays were not cache-based machines. COAS had no cache concepts in it at all. It was all buffering. So then when we started caching, we set the cache page sizes to disk geometry. So that when I pull it into this cache buffer and then I have to send it off to disk, it's going to be in a friendly number to fill up my rotation track and make it as efficient as possible. But then somebody figured out zone bit drives are coming into play. How can I size these things to the disk? I've got different sized disks out there now. In fact, the same disk has different sizes depending upon where I am on the drive. And somebody else came along and said, well, geez, the purpose of a cache is to reuse my data. So step 3 was size the file system and cache pages to the application request size. And the only way in Irix you can do that is with par-s. Par-s, and then you can grep for read or write and see the actual system calls. Third argument is number of bytes or the size of the request. So along they came and said, well, since I'm reusing cache, the I/O path that should be hot is user to cache, not cache to disk, so I should make it friendly to the application request size. Well, nowadays, this is what we're doing, is simply ask the OS. And there's an FNCTL system call that allows you to tell the OS, please tell me, what's a friendly I/O number? What is a well-formed number for your particular configuration? So when I do a BIO size, I should be able to use FNCTL and ask it, what's a good size? What do you want me to give you the data in terms of chunk sizes? Okay. And that's kind of the history of the way things went along. And the key break-off here was how could we size it to disks when we've got all kinds of different disks out there, you know, in all kinds of different markets. And if I'm writing a third-party vendor application, they're not going to write it just for the high-end Cray disks or anything like that. So nowadays, we're simply asking. And it's up to the application to do that. Anyways, on the logging area then, the logging, it does write-ahead logging of updates to the metadata, any inodes, directory blocks, free space blocks, inode B trees, extent maps, allocation group headers, and superblock. Any sort of changes in there are logged in the journaling log, and then if I take an interruption, I can use that information to rebuild my file system, so to speak, relink things up. So the XLV Volume Manager is what actually understands the geometry of how this file system was put together. Okay, in the simplest case, it may be a single disk partition, or in worst cases, it could be scattered all over the place. Physical partitions could be concatenated, they can be striped, or they can be mirrored. And mirroring and plexing are the same thing. So when I put this volume together with XFS MakeFS or something like that, I may have a data portion, a log portion, and a real-time portion. The data portion is required. And then out of that data portion, I may have various plexes, and each plex would then be an optional mirror. And then within each plex, I may have several volume elements that are put together to create that actual file system. And then each volume element could be actually several partitions that were put together to create the volume element. So for example, I was talking about I could do 4 wide 4 times. So I may have 4 volume elements with 4 striped disks within each volume element. And then I'd be able to round robin among those 4 different striped groups. However, again, you may be better off going 2 wide and having 8 of them or something like that. What you want to try to do when you're doing striping is to get the stripe width to match your request sizes. So let's see, volumes allows us to create files that span more than one physical disk. These volumes behave like regular disk partitions, and file systems and applications can access the volumes rather than the individual disk partitions. In each logical volume, we have subvolumes, which are composed of the physical partitions that can be either concatenated together, plexed together, striped, or all 3. I can stripe them, then cat them, then plex them. I can put all 3, build a file system that has all 3 properties with them. Now remember, plexing or mirroring is for reliability and it's going to take twice the disk space. So a lot of sites avoid mirroring because it's got to be twice the cost of my disk farm. So instead they go off to RAID devices and do RAID 3 or RAID 5, which is not a redundant copy of the data anymore, but fire code that's generated. Problem with RAID 3 and 5 is I have to generate the fire code. If I write hello mom, it's going to take time to generate the fire code and it's not worth it. If I move a terabyte of data, it is worth it. So with RAID 3 and 5, your large transfers are beneficial, but your small transfers are bad. And if you're reading more than writing, they're good, but if you're writing more than reading, they can be bad, because now you have to generate that fire code.
Is the fire code generation that much of a hit? Because it seems to me that that's almost a flow through the hardware.
We've always buried it within our hardware, yes. But
and if you've got a RAID controller doing that for you, it's almost a non-issue. And the generation happens just as much on
sure.
as on RAID.
Now on RAID 5, you've got what's called write penalty as well. But in general, what I'm saying is that RAID 3s and 5s were not designed for writes. They were designed for large sequential streaming reads. And that's where they pay off. Okay. And the first plex is considered to be the original. You can have up to 4 plexes that are mirrors. The plexes are individually organized. Plexes may be added or detached as needed. The root file system can be plexed, but obviously you put that on a different disk drive. And a plex can have up to 128 volume elements in it, and a volume element can have up to 100 partitions within it that are either concatenated or striped. Okay? So concatenation is used to build large file systems. You can build arbitrarily large volumes up to a 64-bit limit, a maximum of 100 disk partitions, and 128 volume elements. This is useful for creating a file system that's larger than a single disk drive. And a logical volume is constructed by concatenation of these multiple partitions, and they, again, behave like a single partition file system. And the volume manager is responsible for translating the logical addresses into the real disk addresses. And in this example, they're doing a non-striped disk partition. Physical disk partitions are holding your file system blocks, in this case 300,000, so it looks like they're filling up the first drive, going from 0, 1, 2, 3 up to byte 99999. Then they fall over to the second drive, then they fall over to the third drive. Anyway. Whereas striping now, in this example, we're going to take the drive and break it up into chunks and send the first chunk off. Note what they've got here. I don't like this example because they're doing it block by block. We'd have to have a real small stripe unit to be able to accomplish this. Stripe unit's 128, not 1 or 2 or 3 like they've got here. So what they're doing here is taking each block and distributing them round robin among the drives in the stripe group. So block 0 went there, block 1 went there, block 2 went there. I'd have to have a stripe unit size of 1 to accomplish this. The default is 64. So it goes 0 through 64 to the first device, 65 through 128 to the second device, that sort of thing. If my transfer size was less than 64 kbyte, I'm only going to end up in the first stripe unit of the partition. So if all my I/O is lots of little I/O, like 5 kbyte transfers, I may end up pounding on the first drive of the stripe group and never take advantage of the bandwidth that the other drives give me because my transfer size is too small. And that's the problem in the database market with striping. Striping doesn't help you there. As far as I'm concerned, striping started in Minnesota, Wisconsin with Control Data and Cray doing some of the first striping. Then Berkeley came along and put a name on it and put reliability in there too and called it RAID. They created RAID 0, which is JBOD, just a bunch of disks. RAID 1 then was mirroring. And then we got into RAID 3s and 5s, which were designed to save space but still have reliability. And a lot of sites will ship and default with a RAID 3 or RAID 5 when in fact they really should be at a RAID 01, but they want to save disk space. But they want striping, but they may stripe 10 wide within the RAID cabinet, and you really need maybe 1 or 2 wide because of the nature of the I/O that you're doing. So a striped disk is a volume that's created in such a way to distribute the data blocks across 2 or more physical drives, but it's basically a striped I/O performance approach is n times the I/O bandwidth, where n is the striped device width. In other words, how many disk drives are in there. The striped device width is the number of physical drives in the stripe group. And then the stripe unit is the smallest chunk that I'm going to break it up into, also called the step size. So I take a request and break it up into stripe unit sizes and then send it off in parallel to the stripe device width, aligning it to the beginning device on the stripe boundary. Obvious advantage to disk striping is increased bandwidth, not latency. You're tying up all the drives. They're acting as a single drive. Now I'm single-threaded through that file system. Only one request may activate 128 drives, but I'm only going to be using one of them. The rest are going to be basically busy. Now there is an option in 6.5 to turn off alignment. So I don't do boundary alignment to the first stripe group. I don't align to the first device in the stripe group. I can spread it around. It's called no align. But by default, we're aligning and pounding on the first drive all the time. And we have to go over step size to activate the other drives, or go over stripe unit size. So the advantage may be increased bandwidth, but it could hurt you because now if I'm doing lots of little I/O, I've got long wait times to get through that single-threaded file system. A disadvantage to striping is that sequential data scattered across several disks, losing one of the drives damages the striped file. So it's a reliability question as well. Striping makes sense where I/O requests are large. Small requests perform better on non-striped volumes. Okay. And I'm getting into a little battle here with Mountain View where they got this news server striped real wide, but they're doing lots of little inode manipulation and lots of little news articles. And they're trying to distribute and take advantage of VAR news across all the drives, but they're not, and it's striped as a striped group. Generally, when you see a striped group, SAR will show them all behaving the same. They'll look identical. They'll look as a single drive. So that's where striping is often abused. Even in the Cray world, when University of Texas said striping is the greatest thing in the world, and they striped temp and root and home all across all drives. And striping is only as good as the weakest link in the chain. All it takes is one of the drives in the group to have contention, and the whole file system slows down. And then if everyone else is interlocked, if all your file systems are interlocked to one drive, every file system slows down. So if I happen to put every file system on one drive, all I have to do is beat up on that one drive and the whole system comes to a halt. Now in this example, they're doing disk striping where they take this file and they're striping it. 4 is going to this drive, 5 is going to the next one, block 6 is going to the next one. Again, in this example, we're using a block unit size of 1 rather than 128. So the advantage of striped I/O is not evident in this illustration due to the small I/O request. Writing 10 blocks of data to disk may be much more efficient if done to a single drive rather than tying up 3 drives. And also with striping, disk head movement delays are overlapped, possibly providing us enhanced performance. But striping is raising my crossover. Bandwidth times seek plus latency. Seek and latency are staying the same. It's the same drive underneath. But as I add more drives in JBOD, it's the bandwidth that's going up. Therefore, the crossover is going up. And I'm turning it into a bandwidth drive. And a lot of these RAID cabinets are pre-configured for bandwidth, not for latency. Mirroring, so I've got an original plex here, and then it's showing that everything that's echoed off to this drive is going to be shadowed or mirrored off to the other drives. Have up to 4 mirrors, or 3 mirrors plus the original plex. And again, it's for reliability, not necessarily performance. A read could be issued to any plex since all copies are identical unless there's an error reading in one of the plexes. Then we've got a problem. And by the way, there was a case of one site that had got their file system configured, everything was running right, then along they came and said, geez, performance got real bad on the system. What had happened was there was something called RAID agent that writes errors into the syslog. It had crashed, and there was no indication in syslog that they had a hardware failure in the RAID cabinet. So one device was failing with hard errors. There was no syslog indication of it, but the entire striped group was behaving real slowly because of the one drive that was failing within it. And if the RAID agent hadn't crashed, they would have caught it quicker. Guaranteed RAID I/O, basically all metadata is going still in, let's see, what do we got here? The data section, the log section, and the real-time section. So all metadata for my GRIO files are being put on the data section, but then the actual data is off on a GRIO type of section. And again, that's more for video markets and real-time markets. You can read some of this on your own. I haven't worked with GRIO yet. But they do talk about using it for video on demand and stuff like that. And nobody in Egan really is playing with real-time yet. There was some people talking about using it like a primary, secondary, but nobody's doing that yet. Now there are naming conventions for these XLVs. So when you put it together, it's XLV with the volume name, however you've named it, the type of subvolume you have, the plex number, and then the volume element number within that particular XLV file system. So you've got an XLV0 data and an XLV0 log, for example. So allocation groups keep structures to an optimal size, allows parallelization among the groups. For space management, we've got these block-oriented bitmaps that got replaced with B trees instead of bitmaps. We've got large file support. We allow holes in files for kind of a compression type of thing. We can have a large number of files. The inodes can be dynamically allocated and use B trees for looking up the inodes. Large directories. I do have problems with large number of file names in the directory. The problem I've got right now is with sendmail picking in 60,000 inodes within var spool MQ. Var spool MQ is what sendmail reads mail in. It creates 3 inodes per file. On the Crossfire, the Starfire that we had sold off to Sun, it was 3 times faster in manipulating the exact same workload. And all of the locks are manipulating XFS inode. All of the locks that you see everything spinning on are waiting to manipulate the inodes that are going on. Another thing that happened recently on a news server, there is an expire utility that gets rid of old news articles. And the expire had failed, so they had this file system huge with all these inodes for all these articles that were no longer valid but had not been removed from the system yet. Once they restarted it, it took 4 days to restore all those inodes. This fast RM script was running 4 days later, still trying to scrub out expired news articles that should have been caught in a trickle sense rather than all at once. So I do think there's a lot of problems there. And recovery support because of the log mechanism. Allocate files contiguously as possible. I talked about delayed file extent allocation. When we put data into file system buffer cache, it's able to absorb the file and get a better idea how big it is, particularly if you're driving data like a CPU I/O intensive application rather than like an NFS daemon that's trickling stuff. So it allows creation of larger extents by being able to have the cache grow bigger, absorb the whole file, and now I've got a bigger idea of how big it is before I make the allocation. And if you've ever used OSView, OSView has some metrics that describe how often this is occurring. Gives increases in the size of the system, write randomly with no holes. We got large extent support, large files, variable block size. Block size sets minimum unit of fragmentation. Block size is going to control the fragmentation problem. So a small block size would be chosen for file systems with large numbers of small files, and a large block size chosen for file systems with large files. And again, to avoid fragmentation, we're doing delayed allocation and B-tree use to try to avoid it in the first place. But once it's there, the only thing we can do is just like on Unicos, dump, make FS, restore. And that's why on Unicos, when you boot up, it's going to ask you, do I want to make FS temp, for example. I'm going to skip over the mounting type of things right now, or at least that page. When I mount a file system, and again, they're mounting a funny one here. I'm mounting lib and I'm mounting user separately. But when I mount a file system, there is an allocation made out of file system buffer cache. This mount table that occurs, and the mount command prints out this mount table. On Unicos, the mounts can actually fragment your file system. You can actually get more traffic going from cache to disk than user to cache, because I get all these little mounts on the fly. You want to do your mounts when you boot your system. And AutoFS and mounts for NFS will fragment your file system cache real badly on Unicos. On Irix, it's not as bad because Irix can breathe and grow and shrink as it needs to. It's got breathing room, whereas in Unicos, I'm frozen to a finite set of buffers. So on Unicos, I always tell people, don't mount on the fly and unmount it as quickly as possible. Because I could have this file system buffer cache sitting here, whole bunch of buffers, and I create a big file, then I create a little file, then maybe I do the mount, then I create another big file or something like that. Now when I allocate out of cache, it's got to be contiguous. The buffers have to be contiguous. So now all of a sudden I get rid of this file, I get rid of this file, maybe I need to get rid of this file too, but I still got this block here, which means I now got 2 pieces to my cache. Maybe someone comes along now and mounts another file system and it happens to go there. As I keep doing these mounts and allocating out of my cache, I end up breaking it into smaller pieces. Now I try to get that file allocated in cache again, but it's not contiguous anymore. It's not a single piece. So I got to start pushing stuff out. Okay, and I can't push out mount tables. So the only thing I can push out is start pushing everything else out, and maybe this thing gets pushed out, and now I've got room for where that file was to go into that location. And this is what causes severe degradation in interactive performance, both on Craze and on Irix. When you run out of buffers, you can't find a buffer, and you have to start pushing stuff out of cache to get space. When that new server expire failed, I logged in, and with this tool BuffView that we're going to see a little bit later, I could see the entire cache thrashing. The entire contents of the cache were going in and out between a history file and the inode data for the file system. So I had like 100 megabyte thrash going on. And I actually had negative cache hit rates going on at the time, because there was more traffic from cache to disk than user to cache. So mounts can be dangerous because they will fragment your cache. And you really want to do them when you boot the system. And NFS is what creates problems in the Cray world because of all the random mounts that are occurring rather than mounting them hard when you boot the system or something. Let's see. And here it's just trying to show that when I mount the table, mount the file system, some of my super block information is going to go into file system buffer cache. And FS tab controls this mount table, so when I do a mount, I can mount an individual file system or I can mount whatever's in FS tab. And there's a whole bunch of new options with FS tab now to give it information about what to do when it's mounting. The only thing I wish it had was one more saying number of buffers that file system can use. So I could configure 100,000 buffers and say var ADM can only use 100 of them and protect the other buffers from one particular file system. So this is just showing a whole bunch of file systems that got mounted, what the logical file system name was for it. Note that I do have some XLVs that got mounted here. Dev XLV ptemp, dev XLV temp. But the other ones are just raw device names. And also it looks like I've got some NFS mounts that are in this table as well. And DF, we've all used DF. I'm going to skip over that. In Unicode, though, DF does a sync, and Irix it does not. And then transversing file systems. By the way, there's a command called rfind and rfindD. Have you heard of that one? It basically builds a database of the file system tree, and rather than running find, you run rfind. And then rfind goes to the database and looks things up and doesn't have to transverse the file system. Problem is that rfindD has to run all the time to build the database, and that can become a hog. So I tell people don't use find. You know, find is spending a lot of time transversing things. And again, in those scenarios, that NC size environment or systune parameter tells me how much space and memory I can use for all my inodes and my metadata. So by increasing that, my find would go quicker because I'd be able to hold more of my stuff in my directory name lookup cache, my DNLC. So this is just talking about CD and how I transverse file systems. Determine the inode is a directory. If it's a mount point, check if it's an inode, locate the path. For small directories, look at the inode for a matching file name. For large directories, chase down the B tree. Then issue an IO request, and then use the directory B tree to search for the path. When found, the location of the inode is now in the directory entry. And that's what I'm trying to control with NC size, is the size of this directory. And if the Commodus inode does not already reside in memory, I have to go off to disk to get it. On a news server where I've got an inode per news article, I may want to increase NC size to try to hold more things in memory. So the majority of my memory footprint is for my metadata, because that's the stuff that I'm working with the most, the stuff that I'm reusing all the time. Now, if somebody starts abusing a file system, we can implement quotas. File system quotas are a separate module that you have to load in. When you mount your file system, you can set up your quotas. So it provides a mechanism to control usage of your disk space to prevent somebody from filling up their file systems. Home directories, for example, often have a very, very small quota on them so that the people have to get it off the compute server and off onto an NFS server or something. And what's commonly happening at these sites is they make their homes small, but then they create a file system called /archive. And /archive is an NFS mounted file system to the entire cluster. And then I move my data from temp to /archive, and I run data migration on /archive to keep it bottomless. Now, if you're doing large sequential transfers, there's a new product in Unicos that came from Irix called Bulk Data Service, or BDS. And it basically ups the transfer size and bypasses file system buffer cache. So if I'm doing large sequential transfers of data from temp to /archive, Bulk Data Service is a product you run on top of NFS. And then you're doing bigger transfers and you're not spending all your time with protocol. There'll be a little bit about BDS tomorrow. So we try to use quotas to keep them down in their home, force them to run their applications in a file system designed for either capacity or bandwidth. And then, for example, we do I/O in /scratch and then move it to /archive, which was designed for bandwidth or designed for capacity, not bandwidth. So you can set it on a per user basis on any file system. Each file system is separate. Warns users when they exceed their allotted limit. There are two quotas imposed, the amount of space and the number of inodes. And then each quota has 4 associated values: the current usage, the soft limit, in other words, the number of 1K blocks the user is expected to remain below, a hard limit that you cannot exceed, and a time limit. And basically, if a user exceeds the soft limit, a timer is enabled, allowing you to exceed the soft limit temporarily. But if you're over that limit for a long time, then you're going to get a hard limit reach. And exceeding a hard limit or timeout generally means the user job is killed or aborted due to a quota limit problem. And with quotas, the quota command is the user interface to see what you've got. Super user can also see, user can see their own limits, but the super user can see everything. And ed quota edits the user quotas. ACTL manipulates the quotas. There's a quota on and quota off to turn it on and off when you boot the system. And there's a report quota for a summary report. The next piece is about links. I think we can skip over that real quickly. A hard link is in the same file system. In other words, I can have one inode, 2 entries pointing to the same actual data. Whereas a soft link or a symbolic link goes across file systems. And then when you are doing links, we'd already gone through some of this stuff earlier, but when you're doing links, there's this link counter that's incremented, and your ls command, ls-l, printed out the number of links that are associated with that file name. And the rm command is what unlinks it. It actually makes a system call named unlink. But again, the data is not removed until all name pointers to the inodes are all gone. And here a soft link, ln-s, is a symbolic link, and again, the advantage there is it goes across the file system. It goes to a different file system, for example. Their intended purpose is to cross the file system. And there is a Irix parameter for the number of links, the maximum number of links to a file. And by default, it's set to 8. So if you exceed 8 links, you may start getting error messages. And here we're just following the soft link. We've got the directory name lookup cache entry. It is a symbolic link. So the data is not actually there. The file name is, the name of the link is, and then it goes off to the symbolic links inode. And in there, it's actually then pointing to the data block for the symbolic link. And then on the target file systems inode, on the target where we were before, if I did an ls-l, we would actually see the link going back to the other file. And the link counter would not be incremented in that particular file system because it's linked to something else. And lastly, /proc, I think that's the last page. /proc is simply the way of reading a process and treating it like a file. Where are we in time? And we're at about 4:30. Anyway, /proc is a way of reading your A.out space, user addressable space. It's also a way of looking at your user.h, your process table entries, things like that. There are tools out there that use /proc, like gmem usage will go into /proc to get data. But in general, scientific applications and real-world applications don't use it. It's typically system-type tools that use /proc. Okay. Now, since we're so close to 4:30, there's no sense in going on, besides the yawning. So let's pick up tomorrow morning at 8:30, and we're going to talk about I/O management in the morning, and then we're going to wrap up with all those miscellaneous pieces in the afternoon. But I do still plan on going tomorrow afternoon. I'd like to get out at 4 too, but I'm still looking at 4 or 4:30 finish time tomorrow. So we'll see you tomorrow morning.